This started, right? Nobody's joined apparently. So I guess we're about ready to get started. Are there any questions or comments before we start?
Focus on the mutual information part.
Yeah, we'll do that tomorrow.
Okay.
Oh, that was on the quiz for today, right? Yeah, but we'll do it tomorrow. For sure. Any other questions, comments? How are people feeling about the workload? You can be honest.
It's a lot.
Like, as in too much? Or is it it's still too much? Okay. Because the labs, is it the labs that are taking too long? Or it's just the study load?
They're okay, but sometimes you don't have time to do them in the time we're supposed to do them, and then you have to like redo them. For the machine learning, we have to redo the whole lab. So.
Yeah, the machine learning, we know that was a problem. But even after they fixed it, you think it was still too much? Because didn't he fix the quiz and make it shorter?
I think we're done it yet.
Oh, I see.
Oh, we have to do it again?
Yeah.
I don't know. Ask Gabriele what the solution was.
Yeah, it's much easier to do this time, and it doesn't have any straight errors in it.
Okay. Like I said, I really don't know where it ended up, so just talk to Gabriele about that one. But do you think in general it's more the labs or more the theory that's... The theory is too heavy. Okay.
It's too much reading and not enough time to do quality work on the reading.
I see.
It's too much quantity of reading and not so you can't focus on quality.
Are you thinking?
I mean, I think it's both. If you do have so much time in the computer sessions, we would have more time to do the theory and vice versa.
Okay. Okay, well, thank you for your comments. The only thing we can do is like cancel stuff, so I'll have to think about that. But it's good to know.
There won't really get a break between the lecture and the lab, so it's about 5 hours of continuous.
And then which leaves you like 3 hours to study.
And it's kind of tiring to go back and do more reading at the end of the day.
Yeah.
But I also think it's not about spending the time, which is a lot, but I wouldn't mind spending so much time if I could actually read up on this stuff and do it in more depth and more detail, but it's just the quantity, so it's just getting the reading done, and by then the day is over. So I wouldn't mind spending much time, but I would rather read more detailed and spend more time on the individual topics instead of covering so many topics and just covering them to have them covered instead of covering them and really getting them. At least for me, I don't know about the others, but...
Okay. Well, like I said, let me take a look at that and see what we can do. Thank you for your comments. Shall we start, or are there any other comments? Yes, so we're going to do secondary structure prediction, the first half. This is going to be secondary structure prediction both of proteins and RNA. Can anybody tell me why we should do secondary structure prediction? What utility could this have?
If you can't make crystals.
Sorry?
If you can't make crystals, for example.
If you can't make crystals. Right. So crystallography, is it hard or easy?
Hard.
Yeah, it's hard. Even today it's hard, right? So yeah, I mean, structural information is the highest grade information, but it's the most expensive, sometimes the hardest to get. Or like pretty much always the hardest to get. what else can secondary structure do for us? Secondary structure predictions. I mean, you kind of said it all there, but what can you do with secondary structure predictions, even if it doesn't give you the full 3D structure? It can give you a little bit about function, right? Like maybe you know this, I don't know, this active site needs TLCs for some reason. Maybe it has to fit in a major group of DNA or something. Anything else?
I think maybe you want to recognize common patterns in secondary.
Yeah, sure. Sure. I mean, you might be able to show homology even if the sequence identity is not high enough. Absolutely. So those are all good reasons. And these are more or less what I'm saying here. And so today what we're going to do is going to talk about secondary structure prediction of proteins. We're going to have to talk about, what's our gold standard. Does anybody know what a gold standard is? Somebody want to tell me what gold standard is? It's our, as close as we can get to the truth, right? So some very high quality annotation that we trust and that we're going to compare our computational methods against. By and large, these are manually annotated. These are manual annotations. Anyway, so we're going to talk about that, how we compile our training data sets. And we're going to talk about what's the difference between a secondary structure assignment and prediction, right? And so it's surprising how many people work in this and then don't get this concept clear right off. So secondary structure assignment is what you do when you have the crystal, when you have the structure in front of you, and you say, oh, this is alpha helix, this is beta sheet. I hear a lot of people run DSSP on this structure and say, oh, I predicted this is alpha helix. Well, you didn't really predict it. That's sort of like saying you predicted rain because you walked outside and it's raining. You detected rain, or you labeled rain. Anyway, but we're going to talk about secondary structure assignment as well as prediction. And there's some measures of quality that will tell us how well we did. And then we'll go into the statistical methods for secondary structure prediction. We're not going to get to the neural networks today, but I think we'll get to them tomorrow. And then there's more proteins here. We do coils. And then we go into RNA. Both of these are tomorrow. But we're not going to do transmembrane proteins. Not because they're not worthwhile, but rather because we have an expert giving a whole lecture on that, so Gunnar von Heine. So it turns out Stockholm is a big center for transmembrane helix prediction and transmembrane proteins in general. Okay. So how do we assign secondary structure? Like, what does it mean? Like when I say, oh, this thing is an alpha helix. What does that mean? Like, can you give me an objective, concise definition of what an alpha helix is? If I want to try. You want to try, Joao, or you, whatever. Go ahead.
It's a sequence of amino acids whose torsion angles are defined by 60-60.
That's very good. Yes.
And
So,
the amines of the backbone are always pointing towards the N-terminal. The carboxyles pointing towards the C-terminal.
Okay, that's good.
And the side chains are hydrophobic hydrogen bonds every 4 residues.
Exactly. So reaching I and I plus 4. So you said two things that are used for secondary structure assignment programs: hydrogen bonding and torsion angles, backbone torsion angles. Turns out we don't really need to worry about the side chains because the side chains are dictated by the backbone torsion angles. We know which way the side chains are going to point if we know the torsion angles. And we actually know where the hydrogen bonds are going to be if we know where the torsion angles are. But we use both, and actually it's going to help us a little bit if we use both as opposed to just using one. And then, so that's the case for alpha helices. It's also the case for beta sheets, right? So there's different torsion angles and different hydrogen pulses, but they're the same quantities that we're looking at. And we're going to talk a little bit about the gold standard. And so these are the quantities that we're measuring when we're trying to assign a secondary structure. But initially, before we had secondary structure assignment programs, it was basically a crystallographer looking at the structure and saying, this is an alpha helix, this is a beta sheet. Now, is there a hard boundary between what makes an alpha helix, let's say, and what makes a random coil? That's right. Anyone else? That's right. Is it clear? Is it always clear, given a particular residue, if it's an alpha helix or if it's a random coil? Are you saying?
I'd say no.
No?
Because it always depends on the environment and the adjacent amino acids. Like, even if I have a strong helix former, but in an environment where all other amino acids are not very likely to form a helix.
Mm-hmm. Well, what about if you have the structure? Like you're looking at it, you know the coordinates of all the atoms. Is it clear which secondary structure a certain residue is in? Is it always clear? Like let's say I give you the structure of, I don't know, ribose binding protein. I say, okay, look at residue 136 and tell me if it's an alpha helix or random coil or beta sheet. Are you always going to be able to assign?
No.
Why not? As well.
Certain residues are more likely to be in alpha helixes, right? Or that wouldn't appear in alpha helixes.
Sure. Sure, but let's say you have the coordinates. You're looking at it. You can see all the atoms.
I guess it depends how many. If you have a helix that's like 3 residues long, then is it a helix?
Sure. I mean, especially at the ends of the helices. What's happening at the ends of the helices?
Yeah, exactly. I guess that's the whole.
Yeah, it's like thermal fraying. Maybe the middle residue you can say, oh, that's for sure an alpha helix. But the ones at the end, they're not necessarily following they're not necessarily an alpha helical part of the Ramachandran plot. But it's hard to say because there's no hard boundary between the alpha helical part and the non-alpha helical part. There's a continuous drop off, and so it's just up to you let's say as a methods developer to define where you want that cutoff to be. But there's no underlying truth. There's no underlying fact of the matter. It just matters semantics or definition. And different people, initially the crystallographers just had different styles of thinking, and then later when people made methods, they drew the cutoffs differently. So even the gold standard annotation is still open to debate, right? Because again, we're talking about continuous quantities, not discrete ones. Okay. Okay, so how do we assign secondary structure? First method to be developed was this DSSP, and what it was based on was hydrogen bonding, right? So we're saying that for alpha helices and beta sheets, we're expecting to see a certain pattern of hydrogen bonds, and so the thinking was, okay, let's just find all the hydrogen bonds in some structure, and then see if they follow a pattern that's consistent with that, right? And and this is all it did. It didn't look at torsion angles, and even so, it's surprisingly good. But it used a model for hydrogen bonds that was based on distance and angle, right? So you measure the angle. Let's say this hydrogen is making with its parent atom with respect to whatever the hydrogen bond acceptor is. Which is pretty much going to be an oxygen, carboxyl oxygen, and then it has a distance, like the distance between a hydrogen. Well, I guess they use And so the idea is that for an ideal angle, you have a certain cutoff, but you can even have a hydrogen bond at a non-ideal angle. It's just that it'll become energetically unfavorable much sooner. And so is it clear where's the endpoint of a hydrogen bond here? This is a line at which the energy becomes there's some minus 0.5 kilocalories per mole right here. Right? After this, it starts to approach zero. So basically no interaction. But so is it clear where the line is between having a hydrogen bond and not having a hydrogen bond? Like you're basically looking at a continuous quantity. And right here, I don't know, it might be an inflection point, or they might have just arbitrarily said minus 0.5. But even right here, you might say, oh well, it's kind of weak for a different physical chemist criteria. That might no longer be a hydrogen bond. But anyway, they chose a cutoff at which they would accept a certain combination of angle and distance to be a hydrogen bond, and that would go into this map of hydrogen bonds. The point is that you make a little bit of difference in that boundary, and you can get a slightly different result. And then in the case of so then if they see a pattern here, we say, okay, residue I has a hydrogen bond with residue I plus 3, and this is something that's repeated over a certain number of residues. And then they say, okay, we have an I plus 3 helix, right? And if it's repeated from between I and I plus 4 for a certain number of residues, then they would say, okay, this is a 4-turn helix, and so on. And then they would do something different, where they would say, well, now we're no longer looking at a fixed gap between residues, or rather, we're looking at some gaps, which is let's say this is residue I, this is I plus N, right? You see a hydrogen bond, and then you get I plus 1 and I plus N minus 1, and we see, oh, there's a couple hydrogen bonds there, and so on. We can annotate that and say, oh, that's an anti-parallel pair of beta strokes. Is there any limit to how big this N could be?
No, because it depends on the rest of the structure of the protein.
The entire protein could be this N, right? This could be the N terminus, this could be C terminus. Okay. And so, like I said, that would yes, please.
Could you go back to the alpha helix? So yeah, exactly. How do you know that there are hydrogen bonds between the third or the fourth? Is it because of the atomic positions that we know? Okay.
Yes. So here we're talking about secondary structure assignment. You have the coordinates, you're looking at the structure, and you just want to label it. Even though, as I say, there's still, it can still be debatable, and that's why we have more than one method, and they can give you slightly different results. So the next method is called STRIDE. And their gold standard was again, crystallographer provided secondary structure assignment. But by then DSSP already existed, so maybe some authors used DSSP to assign the secondary structure that they reported to the PDB. And so they get rid of those structures, so they're only using manual assignment. Generally a good idea. Like, you generally do not want to train one computational method on the results of another computational method. And then similar to DSSP, they use this model of the hydrogen bond, which evokes one angle and one distance. But in addition, they use the Raman-Chandran plot. Right? So you can see here we've got above alpha helix, and with this, what you're looking at here is a collection of residues in annotated alpha helices, and it's a histogram of torsion angles, right? So basically, I think you can pretty much agree that there's some sort of circle that we can draw around this big bump, and that to us is an alpha helix, right? And then similarly for the beta sheet, there's some reasonable boundary that we can find that would say, okay, that's a beta sheet. Remember, this is periodic, right? So this is actually one bump, not two. And so Stride uses these two. Oops. These two together. And then here what you're looking at is the agreement between Stride and DSSP, right? So, or not the agreement, but rather the performance. So each dot is, let's say this dot is what percentage DSSP got right, so in this case like 92%, and what percentage Stride got right, so something like 78%, right? And so you can see that there were some dots that DSSP did better, right? Those are the ones that are the unfilled squares. And then there are some dots that Stride got better. Right. So where does DSSP do better? Do you see what I'm saying with these dots telling you which one is better? So each dot has a score, like how many of the residues DSSP assigned correctly, right? So if it goes through and it said like there's 100 residue protein and it got 90% of them were assigned correctly, and there were some that disagreed with the crystallographer's annotation, like another 10%, then the score for that one would have been 90, right? Let's say like this case. And then you assign the secondary structure of DSSP, and DSSP might actually do worse, right? They might say, oh, well, DSSP only got something like 80% correct, right? And so that tells you where this dot gets placed. So anything that's above this diagonal, DSSP did better, right? Can you see where DSSP did better and where it did worse? What region, like what sort of cases is DSSP better at? Cases where both methods did pretty well, or cases where both methods did pretty poorly? So this is where I see a lot of white dots, and so this is where everybody, where you're getting basically 90%, 80% of the assignment correct with respect to the gold standard. And then Stride is better down here, where both methods did poorly. So basically, like if you have, the way I interpret this is if you have structures where it's debatable, like maybe at the ends of helices, or things that are on the boundary between one type of secondary structure and another, then Stride did a bit better, right? And it kind of makes sense because it has more information that it's looking at. But in general, if you make a new method, what you're trying to do is go after the harder cases. Like there's less of a point in trying to be really good at something where other people are already really good. Okay, and then there's a question. Yes, question.
Maybe you said it was, what's the difference between the dark and the...
Oh, so the dark ones are the ones where Stride did better.
Okay.
Because like for example here, this dot, Stride got like, I don't know, 85% correct. And DSSP got like 82% correct, something like that. Yes?
So you're saying that Stride does better when it's the part of the protein that's very unsure of?
Yes, the borderline cases. Like the cases that are a little bit harder to assign. Okay, and so how do we assess the accuracy? So the easiest thing to do is just say, okay, for each residue, how likely is it that I signed it correctly? Right, that's called Q3. And actually, if you just know how many alpha helices there are in the world and how many beta sheets there are in the world and how many coils, like you would just guess based on those probabilities, you get 38% correct, right? And so if your method gets 30%, then it's just random, right? So you have to do better than that. But this way of just adding up residue by residue, which percentage I got right, has a couple of pitfalls, right? So for instance, let's say this is your gold standard secondary structure: helix, beta sheet, helix. Right? And then you have one assignment method, or I don't know, maybe a prediction method. And I said, okay, there's a helix here, beta sheet here, but didn't quite get the boundaries right. Then there's another method that it got the boundaries perfectly for this helix and this helix, even for this beta sheet. Like it says, starts here, but it's the wrong kind, right? It predicted it or assigned it as a helix. Same thing here. Which method do you think is more useful? Sorry?
Prediction 1.
Yes, exactly. Because at least got the right kind of secondary structure, which is what you care about. You might not care so much about the boundary cases. Which one do you think had a better score?
Second one.
That's your guess? So they both got the same score. Yeah, I mean the second one because they got the boundaries right, and the first one because it got the right secondary structure. But I think everybody seems to agree that the one that's useful is this guy. So maybe what's wrong is our scoring method, right? You know, maybe Q3 doesn't say everything. It's a little oversimplified. And so people came up with this alternative called SOV, segment overlap. And basically this introduces this thing called forgiveness, right? So that's kind of like an exam, like if you got 80% of the question, the teacher would just give you 100% of the credit. I mean, that'd be kind of nice sometimes. In this case, it means that if you got, let's say, three residues right out of a 4 residue beta sheet, and let's say your forgiveness is 2, then that means you can get 1 or 2 residues for free, right? So that means that I observe that if I change this to beta sheet, then I get a perfect score, right? So I go ahead and allow myself to do that. It's like a little fudge factor, right? And then I go here to the helix, and my forgiveness is still 2, right? So I can change this to a helix and change this to a coil, you know, and then I can give myself a perfect score there again, right? Because this score is the minimum overlap over the maximum overlap, right? And so the minimum overlap, let's say here would have been 3, and the maximum overlap would have been 4, but I forgave myself on this end, and so actually maximum and minimum are now the same, and so I've got a perfect score on that. So you don't need to worry about the details of this. It's just the point is it gives you a little bit of flexibility, and it rewards you for getting most of the secondary structure correct. Right? And it forgives you a little bit on the boundaries. How do you think it does here? What kind of, do you think we do well with SOV over here? Try. I feel like some of you in the middle row there might know. How about you?
I mean, you align 3 out of the 6 because 2
only aligned with forgiveness too?
Yeah, well, I mean, it depends on things on how you do this, but I think the way you're supposed to do it is you just choose one of these. You say, okay, this versus that, and then I can extend this and change the C to an H, and so it ends up not giving you a very good score, right? It gives you like 2 out of 6, and so this ratio is like you get like a third of a point. And so in this case, actually, Q3 would have given you a better score. So it's just like, you know, alternatives, none of these scoring systems is perfect, but the real, I mean, it's not that I want you to memorize this formula by any means. It's more to give you this idea that when you read a bioinformatical method or when you write one, there's all sorts of ways to evaluate your results, to compare your prediction to the experiment, and you should be very skeptical about this because people do all sorts of things that are just crazy. Like my favorite is something like this, where they did this. Like they have this thing that predicts some energy, like they say some binding energy, and it says, okay, predicted and experiment. And it kind of looks like that. Does that look like it's correlated? Maybe? Just, yeah, maybe it is, right? I mean, it's sort of kind of some kind of slope. And then you read the caption or the footnote somewhere in the text, and it says, oh, this is after we took out all the outliers. Guess what their definition of outlier was? It's the 10% of the data set where we did worst. Right? So their original data set could have looked like this. Right? And then they did this. Throw that away, throw that away. Got a method. So I mean, the paper I read wasn't quite this bad, but come on, defining outliers as something that doesn't, where your theory doesn't fit the data. Anyway, so just be skeptical when you look at these assessments, especially when people are assessing their own methods. Okay, so any questions? Okay, we already talked a bit about specificity, but just to recap, specificity is, or sensitivity is how many true positives you recapitulated out of your gold standard positives, and sensitivity is how many of the true negatives of the total gold standard negatives you correctly assigned as test negatives. And we said that you can't have both ways. Like you can either get a lot of sensitivity and not so much specificity, or vice versa. And it depends on your threshold, right? And actually, next semester when you go to KI, I'm sure you're going to be here all the time because like this, everything about a diagnostic test is sensitivity and specificity. So like for example, this is something I did. I made this predictor. You don't, it's a hinge predictor actually, but it doesn't really matter. Here's your annotation, gold standard annotation, and here's your predictor, right? This red spike. And if you have a strict criterion, that means that you take only the highest scores as being correct, and so you would be very very confident that this is a hinge, and sure enough it is. And if you have really looser criteria, you get more sensitivity, meaning you pick up both hinges, but you also pick up some false positives, right? And the more you go, the more false positives you get. And I think even Arne showed you the ROC curve. He explains to you that that ideally you ROC curve will look like this, right? So area. So there's two measures of merit. One is area under the curve, which you want to be as close to unity as possible. And another is a slope at the origin, right? So that means like how quickly you start to pick up false positives as your criterion gets looser. And you ideally want this slope to be basically vertical, right? But of course it depends on how hard the problem is. The last thing you want is a ROC curve that looks like that, right? That just means random method. Okay. So this the kind of the first attempt at secondary structure prediction was by Chu and Fossman, and what they did was they tabulated how often certain amino acid types occurred in different secondary structure classes. And then they had this heuristic, meaning a set of rules where if they see a certain number of, let's say, helical residues in a row, they would assign helix, and then they would continue the helix until they saw a certain number of non-helical residues, right? And it was kind of hand wavy. It was not very rigorous, but there was nothing. So you know, it got into the history books. But one thing they introduced was the concept of helix breakers, right? And every time you read about helix breakers, there's a slightly different list. So I wouldn't worry about memorizing, you know, lists of helix breaker residues, except for proline and glycine, right? So everybody knows why these guys break helices and beta sheets, right? Why does glycine break a secondary structure? Go ahead. I heard the answer being muttered.
Too flexible.
It's too flexible, right? So there's actually a cost in constraining it. Okay, so we're going to talk now about statistical methods. And so the earliest sort of widely used rigorous method was Gore, or Garnier, Osgothorpe, Robson. And what they did is that they said, okay, well, it's not just the residue type at a given position that affects secondary structure, but it's also all its neighbors, right? Because you can imagine that, you know, if you're position I, then maybe the position I plus 4 also has some effect on whether you're going to be a secondary structure or not, right? If you have two lysines, one I plus 4, maybe they're going to fly apart. I don't know. Well, actually, no. Sorry, I should have said that wrong. They didn't look at pairwise dependency. That's actually a big point. But the point is that they figured that nearby residues had an effect, right? That was the main thing. And technically speaking, they didn't make a naive Bayes classifier, but I would argue it's so close that that for these purposes of this discussion, you can consider it as a naive Bayes, and you really should know. You should know about naive Bayes anyway. So we're going to kind of treat it as a naive Bayes and see if you can see where it's going. But anyway, the main idea is that we have a 17 residue window. So we have the central residue, 8 residues to the left, and 8 residues to the right, and each residue type has a different propensity for a certain secondary structure at the central residue, right? We're always going to be predicting the conformation here and using information from the entire window. Okay. So how does Bayesian analysis work? So we could need a few definitions first. I'm sure you've seen this before, but conditional probability. P of x, vertical pipe y. That means the probability of x given y. Right? So you know y. This reduces your universe, and now you know. Now you ask what's the probability of x in this new universe. The joint probability is written P of x comma y. And this identically equal to this set notation x intersect y. And this will become a little bit clearer graphically in a second. But this is just the probability of observing x and y together. Right, so for example, the probability of observing glycine and alpha helical together. This is the definition of statistical independence. So if P of x comma y, the joint probability of x and y is equal to the product of the marginal probabilities of P of x and P of y, then x and y are independent. Right? And then lastly, we have Bayes' theorem. P of y given x times P of x is equal to P of x given y times P of y. Right? And if you use this a lot and you just want a really quick mnemonic, well, I mean, you just kind of can think, oh, this x likes to be next to the x, and you know whatever's on the right of the pipe likes to be next to be the same as what's in the marginal probability. But to understand how you got that, it's easiest to always go back to this Venn diagram. So this comes from looking at at this and saying, okay, this is my joint probability, P of A comma B, and this is my marginal probability, let's say probability of B, right? And so what's the probability of A given B in terms of these two quantities? You want to tell me? You might want to give it a shot. You? Back there? Joe? Sorry, I don't mean to pick on you, but you kind of look like you had the answer. Maybe I'm being biased. Sorry?
It's a probability of A splitting.
I can't hear you. Were you next to Joe? Oh, you in the back. Sorry.
Yeah, so on there, your probability of A and B is going to be the probability of them both having happened together, so the joint probability over the probability of B already occurring.
Yes, exactly.
A given B happens, you already know that B's happened, so when you take the joint probability of them together and divide by the probability of B, you're accounting for the fact that you already know that it's happened.
Exactly. So, yeah. So I'm sorry, can you say your name once more?
Marcus.
Marcus. So what Marcus is saying is that probability of A given B is probability of A comma B divided by probability of B. So the joint probability divided by the marginal probability of B. And that's because if probability of A given B means that we know B happened. So our universe is B, this thing. And so the probability of A is just this thing. So this thing divided by this bigger thing is probability of A given B. Right? And so what's the probability of B given A? Oops. Go ahead and take this one, Marcus, again.
Yes, it's just the other way around.
Right.
So you basically have the same conditional probability or joint probability in the middle because you know that, and then you divide by probability of A occurring instead because this time you know you're already assuming that A has happened, so you account for that by dividing by that probability over joint probability.
Exactly. So I just flipped A and B. That's all. I mean, this thing here, I could have put B comma A. It's the same thing. Okay, and so now, what's the so basically I observe both sides of both the. Oh well, hopefully you kind of got that. Both sides of these have this quantity P of A comma B, right? One side had this on this denominator, like this, right? And the other one had it one had P of B in the denominator, one had P of A in the denominator. So I'm just going to pass that over to the other side, and I get like this, right? And that's then I can do the same thing to the other side, and that would give you P of B given A, P of A. Does that make sense, or did I lose people with losing my annotations? Okay. So basically, just gazing at this gives you definition of conditional probability, and then you have two equations for A given B and B given A, and then you eliminate the P of the joint probability. And so you basically get a way to switch these two probabilities. And you should just have it. It's just like this because it's so useful. And like for sure, like I say at KI, you're gonna be using this all the time. Am I right? Or you're in the red sweater. I just forget your name from KI. Anyway, maybe whatever. But I'm sure for your classes you'll need this. Okay. Is this all I want to say? Yeah. So that's base theorem. Okay. So this is a simple example. So let's say I go through the metro, go to the metro every day, and I start counting, like I spent a week counting people, right? I didn't actually do this, but let's just say I did. And I say, okay, what's the probability? Like how many people are female in the car, right? Oh, it's about how many people have long hair? And let's say I came up with 0.55. And then I said, how many had long hair and are male? Oh, about 10% of the people in the car. So basically, I can answer a few questions. Like, by the way, I'm not suggesting that women should have long hair, men should have short hair, anything like that. But the point is that that I can then infer all kinds of statistics, right? So first of all, what's the probability of being female with long hair? Just based on these numbers. You was right? Yes, this one. So how much is that? This whole big this oval is 0.55. Long hair. Yes. So 0.45, right? Because they're just two subsets, and they have to add up to 0.55. So yeah, so that's 0.45. What's the probability that I have long hair given that I'm female? You want to tell me? Go ahead.
The 0.45 and divided by 50.
Exactly. So it's, yeah, exactly. Actually, I guess we only have to evaluate that. That's 0.9. All right. And now here's where we need to use Bayes' theorem. And use Bayes' theorem, don't use the Venn diagram. What's the probability that I'm female given that I have long hair? So let's do this up here. Tell me using Bayes' theorem how I'm going to get that quantity. Sorry? By 0.55 or by 0.5? That's actually correct, but you did it just by looking at the Venn diagram, right? Well, I mean, you divided this by that, which is completely correct. Maybe I should have thought of a harder way to do this, but I want you to actually use Bayes' theorem. So I want to see, I want to see the probability of long hair given female in there. Like I want to see. Exactly. How do I use it?
Like it's long hair, comma, female, and then divided by.
Comma or vertical pipe? Oh yes, that's comma. Okay, but okay, fine. Let's just go and do that. Oops. Oy. I really would like someone to use this. PFF given L. Because we computed this earlier, right? This is, well, we have it here, right? And we said that was 0.9. Yes?
Times P of L divided by P of F.
Exactly. So does everybody see how that's just Bayes' theorem? Because before when I showed you Bayes' theorem, P of F was over here, and this is P of F given L, P of L. Right? And so what's this? I'm just going to 0.55, and then this is 0.5, right? And so you can compute that, and that's. Can somebody compute that for me?
2.25 or 2.475. To be exact.
Sure. It should be close to like 90%.
0.9.
0.9 exactly?
0.9.
0.99.
Yeah.
Okay. I mean, obviously these are all fudged numbers, but anyway, that would be the conclusion you would draw, is that if you have long hair, you're very likely to be female. Okay. Okay. Are there any questions about that? Yes.
I don't get where you found this F type L, like how you found that.
This one?
Yeah.
That was just dividing. Yeah, this is one of the marks that got erased. But P of F given L, that was P of F comma L divided by P of L. Right? Does that make sense? It's basically this part divided by this part. Right? And we said this little part was 0.45 and this big part was 0.55. Oh, that's not actually 0.9, I guess. Sorry.
Yeah. That's why I had. Yeah.
So if you compute that, it'll give you something slightly from 0.99. Okay. So is that clear enough? Or okay. Sorry? 0.9? That might be right.
I think you wanted to ask the other way around, and then you just did it to. So what you've written there is right, but you originally asked the F.
Oh.
So that's why.
Sorry, but I think you got the point, right? Sorry about that. Okay, and the next thing we're going to need now is chain rule. And it's the last part we're going to need in order to use naive Bayes. So naive Bayes is effectively nothing more than the assumption of statistical independence, right? For pairwise interactions between residues in this case, or basically inputs. And so the way this works is you've got this quantity that you can tabulate, right? It's called P of C comma x1 blah 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 to xn, right? And in our example, C is a secondary structure, right? And so a particular value of this could be. I'm just not going to use the tablet anymore. A particular value, so this is P of ck comma x1 blah blah all the way to xn. And so a particular value of ck might be helical, right? And then a particular value of x1 might be glycine. And then there's going to be like tryptophan, lysine, blah blah blah. And maybe some cysteine at the end, whatever. These are all residue types. So, is it possible for me to tabulate how often this particular sequence of 17 residues occurs together with alpha helix? Yes?
We have another question about the slide before, because the fourth and the last probability.
In the next slide, you have the answers, and for the last one, and basically female comma long hair and female type long hair, you have the same answer, and it shouldn't be the same.
If it was it last year's slides? I haven't updated them. There could be a mistake in last year's slides.
Yes, that's just as I mentioned.
Because both of them are 0.45 divided by 0.55.
Well, I mean, or it could be that they were. That is fine. You're saying these two are the same?
No,
That
that
last
one and the last one.
Okay.
The last one should be the other one divided by the probability of long hair, right?
Let's just do this. P of F given L is equal to P of F comma L divided by P of L, right? And we do have all these quantities. This is What does this come to? What does this compute to? Wait, what? Okay. I'll upload new slides. I could have made a mistake last time.
Shouldn't we also multiply that by P of F? According to the base case?
No, because there's a typo.
That's what is broken in base, which is the extension of F comma L. Yeah, it's T of D over D by T of D is given because dt is correct.
But it's good that you asked me these questions because I think I can see that you got it now. Alright. So right now? Or do you guys want to ask more questions about this one? What do you think? Are there still questions, or do you want to go on to the next slide?
That's fine, I think.
Come on. I feel like there is some objection back here. Or maybe you just want time to digest it. Fine, let's just go. Okay, so, table. So basically, the question I was asking was, is it possible to tabulate this? Let's say that the probability that the central residue is alpha helical, and that the first residue is glycine, second residue is tryptophan, third residue is lysine, blah blah blah. Right? So a set of like a specific 17 residue sequence and a specific secondary structure or class. Is it possible to tabulate this, like let's say for the entire protein data bank? What do you think? How many, like if my amino acid sequence is 17 residues long, how often would it occur in the protein data bank? Would it occur often? Is that a very specific sequence? Sorry? 17. Probably not, right? I mean, there might be one occurrence, or there might be 0 occurrences, right? So I could definitely tabulate this, but it would be very sparse, and I would need a gigantic table, right? I mean, I would need, there's 20 to the 17 times, let's say 4. That's a pretty big number, right? So those are a lot of classes, and so for me to make a predictor, based on, you know, what happens like for a specific 17 residue sequence, what's the most likely secondary structure type? There's just not enough statistics for that, right? And so this is when we start to make some simplifying assumptions. You know, and of course we lose information when we make assumptions, but this is just there's just not enough data to do it frontally, right? To do real Bayes. And so we do something called naive Bayes, where we assume it actually doesn't matter what specific sequence is, it just matters what's here, what's here, what's here, what's here, but separately, not in combination. And so the way we're going to do this is first we have to break this up somehow, and then I'll show you where the assumption of independence comes in. So chain rule basically says that first of all we can move the C to the end. These parameters can be shuffled. There's no problem with that. And then the first thing we're going to separate out is x1. So we can say that this thing is equal to p of x1 given, p of x1 given x2, x3, blah, 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 all the way to xn and ck times p of all this stuff, all of this, right? P of x2, x3, blah, 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 to xn and ck. You see what I did there?
What's CK?
So ck is your second, in this case it's your secondary structure class. It's the thing you're trying to predict. For
In the formula, like, you already given this one given the other ones, and the CK.
So the CK is the thing you're trying to predict, but when you both stand and say this, you would know what it is.
Is it like a constant you have in terms of like within the formula? What does the CK have to say?
You could think of it. You can think of it as an integer value that can take values from 1 to 4, let's say, depending on how many secondary structure classes you have. Like it could be alpha, helix, beta sheet, random coil.
So it depends on you, and you define the C based on how many you're predicting. Like if you're just taking 2 out of the 4, so you just say C of K is 2.
Yeah, I mean, depending on what secondary classes you have in your definition, right? Because I mean, there are actually all these subsets of maybe you want to even predict I plus 3 helices and I plus 5 helices and so on. Like there's different ways to do even finer grained secondary structure classes. But we're probably just interested in like beta sheet versus random coil versus beta turns versus alpha helixes, right? So that's what Gore did. There's beta turns, alpha helix, beta sheet, and random coil.
That in this case would be 4.
There'll be 4, yes.
Okay. So you multiply that into 4 every time, or like in the case.
Well, first of all, we don't have to worry about what the size or like what these data types are yet. You can just think of them as just arbitrary symbols, right? You don't have to quite yet give it a meaning in that way. But basically, all we did here was say that P of A comma B is equal to P of A given B times P of B, right? Does everybody believe that from the Venn diagram? Okay. And so, except in this case, our B is just this whole list of things, right? So now, this actually is already I'm going to argue that this is actually already something that we can hang on to for a while. And this thing is something that we want to break up, right? So this, we do exactly the same thing, except now we take out x2. This thing is now equal to x2 given x3, x4, blah, blah, up to xn, and ck, right? Times the probability of what? X3, exactly. X3 to xn and ck, right? And we keep doing this, right? Next, we're going to break this thing up. And eventually, all we're going to have left is P, like this thing is eventually going to have a whole bunch of things in it, and P of X n given CK times P of CK, right? And there's going to be a whole bunch of terms that look like this, except they're going to be like, this is going to become 2, 3, 4, 5, this list keeps getting shorter, 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 right? By the way, I'm not going to expect you to reproduce this derivation. But the idea is that you look at this thing and you say, okay, what is this? This is the probability of, let's say, the probability that this is glycine, given that this thing is tryptophan, and this thing is lysine, and this thing is cysteine or whatever, and then this thing is alpha helix, right? And naive Bayes is all about saying, guess what? It's actually irrelevant what residue type is at position 2, right? Like the probability that I'm glycine is only related to secondary structure, right? This guy and this guy are independent of each other. So I just do this. All I'm saying here is that P of x1 comma x2 is P of x1 times P of x2, right? They're independent. Okay, so this thing, by this sweeping assumption, which again you have every right to be skeptical of, now becomes P of x1 given CK, right? And then this thing here, becomes P of x2 given CK, right? And there's going to be a P of x3 given CK, and so on, all the way down to P of x n given CK times P of CK, right? So what I'm saying is that this thing, this joint probability can be expressed this way, and this is something that's much easier this is going to give us better statistics in terms of these are things that are much better populated, right? Because all I'm saying here is for example, what's the probability that I'm glycine at position 1 if I'm in an alpha helix, right? So that's pretty populated, right? I mean, glycine within like 8 residues to the left of an alpha helix. There must be lots of examples of that, right? Roughly like the number of glycines in the PDB divided by 3 or something. Okay, so this is basically naive Bayes. Like all it is you're assuming statistical independence of all your inputs. And yeah, you can write it a bit more tersely as P of, sorry, take this out front, P of CK times the product series of P of Xi given CK, right? And then it turns out that you can just this only gave you this, but this turns out to be proportional to this thing. Do you want to see that last step, or is it enough to say that? What was that? Does this make sense? How this thing basically represents all of that, like, I mean, simplification of that, naive simplification. So basically, what this has is all these probabilities of observing a certain amino acid type at a certain distance point is that there's lots of observations of this, and so it's something that's a little bit easier to do. Like these days, with more sequences and more structures, maybe we can do a little bit better. But anyway, back in the day, they had to just assume statistical independence. You think it's a good assumption to assume statistical independence, like in the case of residues that are nearby? Like, probably not. It's not great, no. So because, for example, let's say, I don't know, arginine is actually pretty good in alpha helices. But what if I have arginine at position I and arginine at position I plus 4? What would that do? That would probably break the alpha helix, right? Because you have light charges that push each other apart. So something that's good here, and there's something that's good over here, but together they're not good, right? So there definitely are pairwise correlations, but we're just sort of sweeping that under the rug for now. And actually, they went through a different derivation in their paper, but I feel like it's not so important. Like you can easily transform this to that with Bayes' theorem. The one thing that's useful is they take the log. And if you take the log of the product series, then you get a sum, and so that's easier to work with because then you can just sum elements. But the point is that you end up getting all these things that you can easily tabulate and you put them into this table, right? And so these numbers are propensities. For example, like this number here is a propensity for glycine to be in the middle of an alpha helix. Or rather, this thing is all these. This whole method is about predicting what secondary structure I have here at position J, right? And so what's saying here, glycine at position J, right at the residue position I'm trying to predict the structure of, that's got a negative number, means that glycine it's very unlikely that this is going to be alpha helix. On the other hand, something like, what is this? Like glutamate, that's perfectly happy in an alpha helix. And then what happens when you're at position J plus 8? So here glycine at position J plus 8, because those 8 residues away from the residue position you're interested in, has much less of an effect, right? So minus 5 means, yeah, it's still a slightly negative effect, but it's very slight. And so you should be able to look at this table, and it should start to make sense to you the more you look at it, right? For instance, let's say, first of all, what's happening as you get away from J? You go in this direction and you go in this direction. What's happening to the numbers?
Getting smaller.
Exactly. Yeah, they're getting smaller in absolute value. So that means that if you're at position 8, either plus 8 or minus 8, you have very little effect on position J. Does that make sense to you? Yeah, I mean, so in case of an alpha helix, you're 2 terms away, so the effect starts to get erased. Yes?
I have a question about, for example, lysine. So because it has a value of 60 or so by J minus 4, and then for J23, if I see correctly, does that mean that it likes to be next to?
That's very interesting. It looks like lysine is actually pretty good at J minus 4, but it's not quite as good at position J. In fact, it's marginal.
Does that mean that it's rather next to an alpha helix than in an alpha helix?
Yeah, it kind of sounds like that, right?
Okay.
I mean, I have no explanation for why. I don't know, maybe it's good at the ends of helices, but not in the middle of helices. I don't know. It's a good observation, though. I haven't noticed that one. And there's actually a few of them that do things like that, right? Like glutamate. Yes, what do you?
How they compute these numbers? Because these I don't see how they consider the position. Like
These I's, this is position. So
it's independent in this case.
so I is equal to minus 8 to plus 8.
Oh, but did you do this for each position?
Yes. basically, for each residue in your protein data bank, you would look 8 residues to the left and count how many times you saw glycine, and you'll get a number like that.
But then, like, you have some kind of sequence, and you have to predict the structure of the sequence. So when you only have the first residue, or do you predict them based on?
Oh, yeah. If you can only do this, I forget exactly what they did, but I think they probably threw away the first 7 residues of each structure. Good question. Other questions? Want a little bit more time to gaze at this table? Any other observations that you make from looking at this? Anything that doesn't make sense? Like about some value that you think is just wrong? Or some value is so right that it just, wow, I didn't think about it this way. Okay, so are there any comments or questions?
Like, this is still secondary structure assignment per se, right?
No, this is prediction, because here, you trained it on a gold standard where you knew the answer, but now when you have a sequence, you can just go to this table and make a prediction, right? So like, let's say, like actually, here's an exercise. Let's say I have this crazy sequence: arginine, 8 arginines, alanine, tyrosine, and then a bunch of lysines. Why don't you tell me what the propensity of alpha helix is for that?
Calculate every single position.
Yeah. Yeah, so basically you start at position I-8 and you look up arginine. Here, 0. Actually, I chose this because it's really easy to compute, right? Arginine is 0 all the way up to like position J minus 3.
It's always 0.
Arginine is 0, 1. It's 0, 1.
It's completely 0. It's 0 till J position.
I can't see this. Anyway, so I'll just believe you. It's 0 all the way to J.
And J is minus 9.
And J is minus 9. Fine, I'll believe you. And then alanine, so it says all zeros, and then alanine is what? 65. And then I have YY, tyrosine. What is that? My eyeballs.
Minus 40, minus 35.
Okay, just add these up on like a notebook or something, and then all lysines. Where's lysines? There we go. I think I chose this to be all zeros. Yeah, like that. Okay, fine. So what does that give you? Minus 10. So, I mean, we don't actually know if we make alpha helical because we have to look at what beta sheet table says, right? You might be just as bad at beta sheet, and then if this is the high score, then we choose alpha helical. But anyway, that's just a procedure for scoring some 17 residue sequence, right? And again, it's going to tell you what the secondary structure should be here. Within this considerable error, of course. Okay, so are we ready to go? Oh, yes, Maria. You filled out this table with structures that you know.
Your sequence, you use this table and see which is the best score?
Yes. Yes. So in this case, this is our sequence, and we can view the propensity for alpha helix at this position, right? We have 3 more tables to do, and then we'll take the best score, right? So if beta sheet got or let's say random coil got a better score, then we would conclude that it's a random coil. questions? Okay, I guess that's it. Any questions about the whole day? Alright, and I'll see you tomorrow.